99% of the Milky Way is invisible, yet it controls everything. Every star you've ever seen, every planet that could harbor life, every atom in your body. All of it exists where it does because of structures you cannot see. Structures that dwarf anything visible. Structures that have been shaping our galaxy for 13 billion years. Right now, you're moving through space at over 500,000 miles per hour, carried by invisible currents in a cosmic ocean you've never seen. The sun isn't just drifting randomly through the galaxy. It's being guided, channeled, protected by an architecture built from matter we can't detect and forces we're only beginning to understand. This isn't speculation. Over the past few decades, astronomers have mapped this invisible framework. They've traced the dark matter filaments that form the skeleton of our galaxy. They've followed rivers of gas, flowing along paths carved by gravity. They've discovered protective bubbles where our solar system drifts in relative safety. And they've connected all of it to a vast cosmic web that spans the entire universe. When you look up at the Milky Way, that pale band of light stretching across the night sky, you're seeing less than 1% of what's actually there. The stars, the glowing gas clouds, they're just decorations on an invisible scaffold. The real galaxy, the structure that determines where stars can form and where life can exist, is completely hidden from view. Before we start this journey, if you find these explorations interesting, a like or subscribe would mean a lot. It tells me someone out there is curious about the same cosmic mysteries I am. And it keeps these videos coming. Now, let's begin by zooming out. Way out. Imagine you're floating above the Milky Way, high enough to see the entire spiral stretched out below you. From this distance, it looks peaceful, organized, a beautiful pinwheel of stars rotating slowly through space, about 100,000 light-years across, with 4 major spiral arms and somewhere between 100 and 400 billion stars. Our sun sits about 26,000 light-years from the center, tucked into a minor arm called the Orion Spur. But now, let's add something to this view. Imagine if you could see all the matter in the galaxy, not just the stuff that glows. If you could see dark matter, that mysterious substance that makes up about 85% of the galaxy's total mass, suddenly, the picture changes completely. The spiral disk you were looking at, that beautiful structure of stars and gas, it's just a thin layer sitting inside something much, much larger. A massive sphere of invisible matter that extends 6 times farther out than the visible disk. This dark matter halo is the real Milky Way. The stars we see are just decorations on a structure we cannot perceive directly. And this halo isn't smooth. It's threaded with filaments, like a vast cosmic spider web. These filaments stretch outward, connecting our galaxy to others. They form a network that spans the entire observable universe. Astronomers call it the cosmic web, and it's the largest structure in existence. Every galaxy in the universe sits at the intersection of these filaments. Where the filaments cross, gravity is strongest, and that's where galaxies form. The space between the filaments, the voids, they're not completely empty, but they're close. Very few galaxies form there because there's not enough matter to pull together under gravity. Our Milky Way sits on one of these filaments, a bridge of dark matter that connects us to the Virgo supercluster, a massive collection of thousands of galaxies about 65 million light-years away. We're actually falling toward Virgo right now, pulled by its gravity, moving at about 600 kilometers per second. But that journey will take billions of years. This cosmic web, these filaments of dark matter, they're not recent discoveries. They formed in the early universe, less than 1 billion years after the Big Bang. Back then, the universe was much more uniform. Matter was spread out almost evenly, with only tiny variations in density. But those tiny variations mattered. Regions that were even slightly denser had slightly more gravity, which pulled in more matter, which increased the gravity further. Over hundreds of millions of years, this process created the filaments and voids we see today. The theory that describes this is called lambda CDM cosmology. Lambda refers to dark energy, the mysterious force causing the universe's expansion to accelerate. CDM stands for cold dark matter, the invisible stuff that makes up most of the mass. This theory predicts exactly the kind of cosmic web we observe, and it's been confirmed by large-scale surveys that map thousands of galaxies across vast regions of space. But here's what makes this relevant to every single star in the Milky Way. These dark matter filaments aren't just roads connecting galaxies, they're channels. Channels that funnel normal matter, the hydrogen and helium gas that makes stars into the galaxy. The filaments guide the flow of gas from the cosmic web into the Milky Way's disk, feeding star formation, maintaining the spiral structure, and ultimately determining where stars can exist. Without this architecture, the Milky Way wouldn't exist. Stars wouldn't have anywhere to form. The visible galaxy we see is entirely dependent on this invisible framework. And there's something else. Our sun doesn't just sit anywhere in this structure. It sits in a very specific location, a region called the local bubble. This is a cavity in space, about 300 light-years across, where the density of gas is much lower than average. It was carved out by supernova explosions that went off millions of years ago, blasting the gas away and creating this protective pocket of near emptiness. The local bubble isn't random. It exists because of how matter flows along the dark matter filaments, how spiral density waves compress gas into certain regions, and how massive stars, which form in those compressed regions, eventually explode and reshape their surroundings. The sun formed near the edge of this bubble, and we've been drifting through it for most of our solar system's existence. This matters more than you might think. The low density inside the local bubble means fewer molecular clouds, fewer massive stars forming nearby, and fewer supernova explosions that could threaten Earth with deadly radiation. It's one reason life had billions of years to evolve without being sterilized by cosmic catastrophes. So when you look up at the night sky, you're not just seeing random stars scattered through empty space. You're seeing the result of an invisible architecture that has been shaping the galaxy for billions of years. An architecture built from dark matter filaments, carved by stellar explosions, channeled by magnetic fields, and constantly evolving as matter flows. Stars are born and the galaxy grows. The discovery of this architecture didn't happen overnight. It took decades of patient observation and theoretical work. In the 1930s, Swiss astrophysicist Fritz Zwicky studied galaxy clusters and noticed something odd. The galaxies were moving too fast. According to the visible matter he could see, they should have flown apart long ago. He proposed the existence of dark matter, unseen mass that provided additional gravity. But his idea was largely ignored. Then in the 1970s, astronomer Vera Rubin made observations that couldn't be dismissed. She measured how fast stars were moving in spiral galaxies and found that stars on the outer edges moved just as fast as stars near the center. This violated everything physicists thought they knew. According to Newton's laws and Einstein's relativity, objects farther from a gravitational center should move slower. But they didn't. The only explanation was a massive halo of invisible matter surrounding each galaxy. Since then, evidence for dark matter has piled up. Gravitational lensing observations show dark matter bending light from distant galaxies. The cosmic microwave background radiation, the afterglow of the Big Bang, has patterns that only make sense if dark matter existed in the early universe. Computer simulations of galaxy formation only produce realistic galaxies when dark matter is included. We still don't know what dark matter is made of. Experiments around the world are searching for the particles, running sensitive detectors deep underground to shield them from cosmic rays. But so far, nothing has been found with certainty. Dark matter remains invisible, detectable only through its gravitational effects. The cosmic web itself was discovered through large-scale galaxy surveys. In the 1980s and 90s, astronomers began mapping the positions of thousands of galaxies across vast regions of space. What they found surprised everyone. Galaxies weren't randomly distributed. They clustered along filaments with enormous voids in between. The universe had structure on the largest scales imaginable. More recent surveys, like the Sloan Digital Sky Survey, which began in 2000, mapped millions of galaxies and revealed the cosmic web in exquisite detail. The filaments stretch across hundreds of millions of light years. The voids are equally vast, regions where few galaxies exist, and at the intersections of multiple filaments, you find massive galaxy clusters, the densest concentrations of matter in the universe. Our Milky Way is part of this structure. The dark matter halo that surrounds our galaxy connects to filaments reaching out to Virgo and beyond. These connections are real. They channel matter. They determine the galaxy's evolution. They're why we exist at all. Over the next 2 hours, we're going to explore this architecture in detail. We'll look at the dark matter filaments that form the skeleton of the galaxy. We'll follow the rivers of gas that flow along them, feeding star formation. We'll dive into the local bubble and understand why our sun's location is so special. We'll see how spiral arms aren't solid structures, but waves of density that sweep through the disk. We'll visit the galactic center, where a supermassive black hole shapes the flow of matter and energy. We'll explore the galactic corona, a vast reservoir of hot gas that surrounds the visible disk. And we'll connect the Milky Way to the larger cosmic web, showing how our galaxy is just one small part of a structure that spans the universe. By the end, you'll understand that the Milky Way isn't just a collection of stars floating in space. It's a dynamic system, controlled by invisible forces, shaped by processes that operate on scales ranging from the size of atoms to the size of the observable universe. And you'll see that our existence here, on this planet, orbiting this star, in this location, at this moment in cosmic history, is the result of an unbroken chain of events stretching back 13.8 billion years, all operating within this hidden architecture. Let's start with the foundation. The dark matter filaments that hold everything together. If you could see dark matter, the Milky Way would look completely different. Instead of a flat spiral disk, you'd see a massive sphere, a halo of invisible matter extending far beyond the visible stars. And within that halo, you'd see structure. Filaments of dark matter running through it, like cables supporting a bridge. Clumps and subhalos, remnants of smaller dark matter halos that merged with ours billions of years ago. And connecting everything, threads reaching outward to other galaxies. This is the skeleton of the Milky Way, the framework that gives the galaxy its shape and holds it together. Dark matter doesn't emit light. It doesn't absorb light. It doesn't interact with electromagnetic radiation at all, as far as we can tell. The only way we know it exists is through gravity. We can see its effects on visible matter. Stars orbiting the galaxy move too fast. According to the laws of physics, they should fly apart, escape the galaxy's gravity. But they don't, because there's far more mass holding them in than we can see. That extra mass is dark matter. Through decades of observations, starting in the 1960s and continuing into the 1980s, astronomers built up detailed rotation curves for spiral galaxies. What they found was consistent across galaxy after galaxy. The rotation speeds didn't drop off with distance as expected. Instead, they stayed remarkably flat, even far beyond the visible edge of the galactic disk. This pattern appeared universal, suggesting something fundamental about galaxy structure that we hadn't understood before. Since then, we've confirmed dark matter's existence in multiple ways. Gravitational lensing, where dark matter bends light from distant galaxies. The cosmic microwave background radiation, which shows patterns that can only be explained if dark matter existed in the early universe. Computer simulations of galaxy formation, which only produce realistic galaxies if dark matter is included. We don't know what dark matter is made of. The leading candidates are theoretical particles like WIMPs, weakly interacting massive particles, or axions, much lighter particles that barely interact with normal matter. Experiments around the world are searching for these particles, but so far, none have been detected with certainty. What we do know is how dark matter behaves. It clumps together under gravity, forming halos around galaxies. These halos aren't smooth. They have structure, shaped by the way dark matter fell together in the early universe. About 13.8 billion years ago, just after the Big Bang, the universe was a hot, dense plasma. As it expanded and cooled, tiny fluctuations in density, probably created by quantum fluctuations during inflation, began to grow. Regions that were slightly denser pulled in more matter. Over time, these regions collapsed under their own gravity. Dark matter, because it doesn't interact with light or normal matter except through gravity, could collapse without resistance. It formed the first structures in the universe, long before normal matter could clump together. These structures were filaments, vast threads of dark matter stretching across millions of light years, with dense nodes where multiple filaments intersected. Normal matter, hydrogen and helium gas, was coupled to photons in the early universe. It couldn't collapse into small structures because radiation pressure kept pushing it apart. But once the universe cooled enough for electrons and protons to combine into neutral atoms, about 380,000 years after the Big Bang, the photons decoupled. Suddenly, normal matter was free to fall into the dark matter structures that were already waiting. This is how the cosmic web formed. Dark matter filaments acting as scaffolding, pulling in normal matter, creating regions where galaxies would eventually form. The Milky Way's dark matter halo is part of this ancient structure. It formed over 13 billion years ago, probably from the merger of several smaller dark matter halos. As these halos collided and merged, they brought their gas with them. That gas settled into a rotating disk, and that's where stars began to form. The halo itself extends about 600,000 light-years from the galactic center. That's 6 times farther than the visible spiral disk, and it contains about 10 times as much mass as all the stars, gas, and dust combined. The dark matter halo is the Milky Way's foundation. Everything else is built on top of it. But the halo isn't static. It has substructure, smaller dark matter halos that merged with ours but haven't completely dissolved yet. These subhalos create gravitational perturbations, tiny tugs on stars and gas clouds that leave observable traces. Astronomers have detected these traces by studying stellar streams, long rivers of stars stretching across the sky. These streams are the remnants of dwarf galaxies that were torn apart by the Milky Way's gravity. As a dwarf galaxy orbits our galaxy, tidal forces stretch it, pulling stars away. Over time, the entire galaxy dissolves, leaving only a stream of stars following the original orbit. By measuring the positions and velocities of stars in these streams, astronomers can map the gravitational field of the Milky Way, including the distribution of dark matter. Some streams have kinks and gaps, regions where something massive passed nearby and disturbed the stars. That something is probably a dark matter subhalo, invisible but massive enough to leave a gravitational signature. This tells us that the Milky Way's dark matter halo is lumpy. It's not a smooth sphere, but a complex structure full of subhalos, each a remnant of the galaxy's violent formation history. And this structure extends beyond the Milky Way. The dark matter halo connects to filaments that reach out to other galaxies. These filaments are the roads along which matter travels. When we look at the cosmic web on large scales, mapping thousands of galaxies across billions of light years, we see that galaxies aren't distributed randomly. They cluster along filaments with vast voids in between. Our Milky Way sits on a filament connecting us to the Virgo supercluster. This filament is part of an even larger structure called the Laniakea supercluster, which contains about 100,000 galaxies spread across 520 million light-years. The Milky Way and our local group of galaxies are on the outer edge of Laniakea, slowly being pulled toward its center of mass. This motion isn't random. It's dictated by the cosmic web. Dark matter filaments create gravity wells, regions where gravity is stronger. Galaxies fall along these filaments, flowing toward the densest regions like water running downhill. The discovery of the Laniakea supercluster came in 2014, when astronomers mapped the motions of thousands of galaxies and traced their flows back to common sources. They found that our local group is part of a much larger system, all flowing toward a central region called the Great Attractor. This region, about 250 million light-years away, contains tens of thousands of galaxies and has a gravitational pull strong enough to affect our motion through space. The dark matter skeleton doesn't just hold the galaxy together. It also determines where the galaxy can grow. Gas flowing into the Milky Way follows the dark matter filaments. When gas reaches the galaxy, it doesn't just rain down evenly. It comes in along specific directions, channeled by the filaments. This creates an uneven distribution of fresh gas in the disk, which affects where new stars can form. Observations show that star formation isn't uniform across the galactic disk. It's concentrated in certain regions, often corresponding to where filaments deliver fresh gas. The spiral arms themselves may be partially maintained by this uneven gas delivery, with gas flowing preferentially into certain arms and keeping them bright with newly formed stars. Computer simulations of galaxy formation show this process in detail. Models like Illustris TNG, which began producing results in 2018, simulate the evolution of the universe from the Big Bang to the present, tracking both dark matter and normal matter. These simulations show that galaxies grow by accreting gas along filaments. When a filament connects a galaxy to a large reservoir of gas, the galaxy grows quickly, forming lots of stars. When the filament runs dry, star formation slows down. The Milky Way has been accreting gas along filaments for billions of years. But that process is slowing down. The cosmic web is aging. The universe is expanding, driven by dark energy, and that expansion is stretching the filaments, reducing their density. Gas that would have flowed into the galaxy in the past is now being pulled away by the expansion. In another 5 to 10 billion years, the filaments feeding the Milky Way will be too diffuse to deliver much gas. Star formation will decline and eventually stop. But for now, the dark matter skeleton is still doing its job, holding the galaxy together, channeling gas into the disk, anchoring the Milky Way to the larger cosmic web. It's the invisible foundation on which everything else rests. The relationship between dark matter and normal matter is crucial. Dark matter provides the gravitational scaffolding, but it's the normal matter, the baryons, that we can actually see and that form stars and planets. Without dark matter, the normal matter would never have clumped together efficiently enough to form galaxies. The universe would be a diffuse soup of gas with very few stars. This is why dark matter is sometimes called the backbone of cosmic structure. It came first, it organized the universe, and it continues to hold everything together. The visible universe, the stars and galaxies and nebulae we photograph with telescopes, is just the tip of the iceberg. The real mass, the real structure, is invisible, and within this foundation, matter flows. Rivers of gas, traced by radio telescopes, follow the dark matter filaments, bringing fresh material to feed the next generation of stars. Let's follow those rivers now. Dark matter provides the skeleton, but it's normal matter, gas and dust, that makes stars. And this gas doesn't just sit still, it flows. Like rivers on Earth follow valleys carved by ancient glaciers. Streams of gas in the Milky Way follow channels carved by dark matter's gravity. These rivers are made mostly of hydrogen, the simplest and most abundant element in the universe. Hydrogen makes up about 75% of all normal matter, and it exists in different forms depending on temperature and density. Cold hydrogen, below about 100 Kelvin, forms molecules. H2, two hydrogen atoms bonded together. Warmer hydrogen, a few thousand Kelvin, exists as neutral atoms. H1, a single proton with a single electron. Hot hydrogen, millions of Kelvin, is ionized. The electron has been stripped away, leaving just the proton. Each form of hydrogen tells us something different about the gas's history and fate. Cold molecular hydrogen is where stars form. It's found in dense clouds, regions where gravity has compressed the gas enough that molecules can survive. These clouds are the nurseries of the galaxy, places where new stars are being born right now. Neutral atomic hydrogen is more widespread. It fills the disk of the galaxy, forming a layer about 600 light-years thick. This neutral hydrogen, called H1, doesn't emit visible light, but it does emit radio waves at a very specific frequency, 21 centimeters. This is caused by a quantum transition in the hydrogen atom. The proton and electron both have spin, and when their spins flip from parallel to antiparallel, the atom releases a photon with a wavelength of 21 centimeters. This 21 centimeter emission is incredibly useful. It allows astronomers to map the distribution of neutral hydrogen throughout the galaxy, even in regions where dust blocks visible light. Massive radio surveys, with names like GALFA, the Galactic Arecibo L-band feed array, and EBICH-IS, the Effelsberg-Bonn H1 survey, have mapped the entire sky in this wavelength, creating detailed three-dimensional maps of neutral hydrogen in the Milky Way. The GALFA survey, conducted at the Arecibo Observatory in Puerto Rico before the telescope's collapse in 2020, provided some of the highest resolution maps of neutral hydrogen ever made. The survey revealed intricate filamentary structures, showing how gas is organized on both large and small scales. What these maps reveal is structure. The neutral hydrogen isn't evenly distributed. It's clumped into filaments and streams, following the spiral arms, flowing into the disk from above and below, and sometimes forming coherent structures that span thousands of light-years. One of the most famous of these structures is the Magellanic Stream. This is a vast ribbon of hydrogen gas stretching across more than half the southern sky, trailing behind the large and small Magellanic Clouds, two small satellite galaxies that orbit the Milky Way. The Magellanic Stream was discovered in the 1970s through radio observations. It contains about 500 million times the mass of the Sun in hydrogen gas, enough to make millions of stars. The stream formed because the Magellanic Clouds are being torn apart by the Milky Way's gravity. As they orbit, tidal forces pull gas away from them, leaving a trail that stretches for hundreds of thousands of light years. This gas is falling into the Milky Way. Over the next few billion years, it will rain down onto the disk, mixing with the existing gas and eventually forming new stars. The Magellanic Stream is one of the rivers feeding the galaxy, bringing fresh material to sustain star formation. But the Magellanic Stream isn't the only one. There are other streams, smaller but still significant. High-velocity clouds, dense clumps of neutral hydrogen moving at speeds that don't match the rotation of the disk. These clouds are falling into the galaxy from the halo, some of them possibly remnants of ancient satellite galaxies that were completely destroyed, leaving only their gas behind. Astronomers have catalogued over 100 high-velocity clouds. Most are small, containing just a few thousand solar masses of hydrogen, but some are much larger. These clouds are important because they represent a continuous infall of fresh gas, helping to sustain star formation over billions of years. One particularly interesting high-velocity cloud is the Smith Cloud. This is a massive structure, about 11,000 light-years long and 2,500 light-years wide, containing about 1 million times the Sun's mass in hydrogen. It's moving toward the disk at high speed and will crash into it in about 30 million years. When it does, the collision will compress the gas, triggering a burst of star formation. Hundreds of thousands of new stars will be born in the region where the Smith Cloud impacts the disk. The Smith Cloud is interesting for another reason. Its chemical composition suggests it came from inside the Milky Way. It has about the same amount of heavy elements, like oxygen and sulfur, as the Sunday. This means the cloud, probably formed in the disk, was blown out into the halo by supernova explosions or stellar winds, and is now falling back. It's part of a cycle, a galactic fountain, where gas is expelled from the disk, cools in the halo, and rains back down. This fountain process is crucial for the galaxy's evolution. Without it, heavy elements forged in stars would stay concentrated in the inner galaxy. The fountain redistributes these elements, mixing them throughout the disk, enriching gas clouds in the outer regions where new stars and planets will form. Our own solar system benefited from this process. The Sun and Earth contain heavy elements like carbon, oxygen, iron, silicon, elements that were created in stars that lived and died before the solar system formed. Those elements were scattered by supernova explosions, mixed by the galactic fountain, and eventually incorporated into the gas cloud that collapsed to form the Sunday. The solar nebula, that disk of gas and dust that surrounded the infant Sun 4.6 billion years ago, was pre-enriched with these materials. Without this enrichment, rocky planets like Earth couldn't have formed. The dust grains that stuck together to build planets required silicon, iron, magnesium, elements that only exist because previous generations of stars processed them. The flow of gas in the Milky Way isn't random. It follows patterns dictated by gravity, rotation, and magnetic fields. The spiral arms, which we'll explore in more detail later, are regions where gas is compressed by density waves. As the density wave passes through, gas clouds collide, compress, and begin collapsing under their own gravity. This triggers star formation, creating the bright blue stars that make spiral arms visible in photographs of other galaxies. But not all gas flows into the disk. Some is expelled. When massive stars die in supernova explosions, they release enormous amounts of energy. This energy heats the surrounding gas to millions of degrees, creating hot bubbles that expand rapidly. If multiple supernovae go off in the same region, these bubbles merge, forming superbubbles that can break through the disk and vent hot gas into the halo. This is what created the local bubble, the low-density region where our sun resides. About 10 to 20 million years ago, a cluster of massive stars formed in our neighborhood. These stars lived fast and died young, exploding as supernovae one after another. The explosions carved out a cavity, pushing the gas away and heating what remained to high temperatures. The hot gas rose into the halo, leaving behind the nearly empty bubble we see today. The local bubble is about 300 light-years across. Its walls are defined by denser regions of gas, places where the expanding bubble stopped because it encountered too much resistance. These walls are actually sites of enhanced star formation. The compression from the expanding bubble triggered the collapse of gas clouds, creating new stars along the bubble's edge. Some of these stars are visible to the naked eye. The Pleiades, a bright cluster of young stars, sits on the edge of the local bubble. So does the Scorpius-Centaurus Association, a group of hot, massive stars. These stars were born in the compressed gas at the bubble's edge, and they're continuing the cycle. Eventually, they too will explode as supernovae, further expanding the bubble or creating new ones. The gas flowing through the galaxy isn't just hydrogen. It also contains helium, about 24% by mass, and trace amounts of heavier elements. These heavier elements, collectively called metals by astronomers, are crucial for planet formation and life. Oxygen, carbon, nitrogen, iron, silicon, all the elements that make up rocky planets and living organisms were created in stars and released into the interstellar medium by supernovae and stellar winds. The distribution of these metals isn't uniform. The inner galaxy is more metal-rich than the outer galaxy because it has had more generations of star formation. Each generation of stars produces more heavy elements, enriching the gas for the next generation. The outer galaxy, where star formation has been slower, is less enriched. Our sun sits in a region with about solar metallicity, meaning the amount of heavy elements in our neighborhood is roughly average for the galaxy. This metallicity was important for the formation of Earth and the other rocky planets. Without enough heavy elements, you can't build large rocky planets. The protoplanetary disk around the young sun contained dust grains made of silicates, iron, and other compounds, and these grains stuck together to form the seeds of planets. The flow of gas in the Milky Way is also shaped by magnetic fields. The interstellar medium isn't just gas and dust. It's a plasma, a mixture of charged particles, and plasmas are affected by magnetic fields. These fields, though incredibly weak by everyday standards, play a significant role on galactic scales. Magnetic fields in the Milky Way follow the spiral arms. They're generated and amplified by a process called the dynamo effect, where the rotation of the disk and convective motions in the gas generate electric currents, which produce magnetic fields. These fields then affect how gas flows, guiding the motion of charged particles and providing pressure that helps support gas clouds against gravitational collapse. Observations from satellites like Planck, which operated from 2009 to 2013 and mapped the entire sky in microwave light, have revealed the structure of magnetic fields in the Milky Way. The fields are stronger and more ordered than scientists expected, suggesting they play a more important role in galactic dynamics than previously thought. The magnetic field strength in the galactic disk is about 6 microgauss, which is about 10,000 times weaker than a refrigerator magnet. But over distances of thousands of light years, these weak fields have significant effects. They channel cosmic rays, high-energy particles that stream through the galaxy. They affect how gas collapses to form stars. And they provide pressure that helps support the disk against gravitational collapse. The gas flowing through the Milky Way is also constantly being recycled. Stars form from cold molecular clouds. They live for millions or billions of years, fusing hydrogen into helium and heavier elements. When they die, they return much of their mass to the interstellar medium, either through gentle stellar winds or violent supernova explosions. This gas mixes with existing gas, cools, and eventually forms new stars. The cycle repeats, generation after generation. Earth's sun is at least a third-generation star, possibly more. It formed from gas that had already been processed through multiple cycles of star birth and death. The presence of heavy elements in the sun and Earth proves this. Those elements didn't exist in the early universe. They had to be created in stars and scattered into space before they could be incorporated into new stars and planets. The rivers of gas in the Milky Way are the bloodstream of the galaxy. They bring fresh material, distribute heavy elements, trigger star formation, and shape the visible structure we observe. Without these flows, the galaxy would be static and dead. Instead, it's dynamic and alive, constantly renewing itself through cycles that have operated for billions of years. The gas we see today in molecular clouds has been recycled through multiple generations of stars, each cycle adding new elements to the mix. And at the heart of this activity, sitting in a protective cavity carved by ancient explosions, is our Sunday. Let's look more closely at this special region. 300 light-years. That's the diameter of the region around our solar system where the gas density is unusually low. This region, called the local bubble, is our cosmic neighborhood. It's a cavity carved out of the interstellar medium by supernova explosions that occurred millions of years ago. To understand why the local bubble matters, you need to understand what space is normally like. The interstellar medium, the gas between the stars, has an average density of about 1 atom per cubic centimeter. That's incredibly thin by Earth standards. The best vacuum we can create in a laboratory has billions of atoms per cubic centimeter. But on galactic scales, that 1 atom per cubic centimeter adds up to significant mass. Inside the local bubble, the density is much lower, about 0.1 atoms per cubic centimeter in some regions. It's not a perfect vacuum, but it's close. And the gas that does exist is hot, about 500,000 Kelvin, which might sound dangerous, but is so diffuse it poses no threat. The local bubble formed between 10 and 20 million years ago. A cluster of massive stars, probably around 50 to 100 of them, formed in a relatively small region of space. These stars were part of what astronomers call an OB association, a loose grouping of hot, massive O-type and B-type stars. These stellar behemoths lived fast, burning through their nuclear fuel in just a few million years, and then exploded as supernovae. Each explosion released about 10 to the 51 ergs of energy, enough to heat millions of solar masses of gas to millions of degrees. The cluster likely formed from a single giant molecular cloud that fragmented into many individual stars. And as the most massive ones began exploding, they created a feedback loop that may have triggered or suppressed additional star formation in the surrounding region. To put that energy in perspective, a single supernova releases more energy in a few seconds than the sun will emit in its entire 10 billion year lifetime. When 50 or 100 of these explosions go off in the same region over just a few million years, The cumulative effect is staggering. The hot gas expands at thousands of kilometers per second, sweeping up the surrounding interstellar medium and blowing a bubble. The hot gas expanded rapidly, blowing a bubble in the interstellar medium. As more supernovae went off, the bubble grew. Eventually, it reached its current size, about 300 light-years across, and stopped expanding because it encountered denser gas that resisted further compression. The walls of the bubble, where the hot interior meets the cooler exterior gas, are regions of enhanced density. These walls are visible in maps of neutral hydrogen and molecular clouds, and they're important because they're sites of active star formation. The compression from the expanding bubble triggers the collapse of gas clouds, creating new stars. Some of these young stars are visible to the naked eye. The Pleiades star cluster, one of the most recognizable patterns in the night sky, sits on the edge of the local bubble. So does the Scorpius-Centaurus Association, a group of bright blue stars visible from the southern hemisphere. These stars were born in the compressed gas at the bubble's edge, and they're continuing the cycle that created the bubble in the first place. Eventually, they'll explode as supernovae, further reshaping the local environment. The Sun wasn't always inside the local bubble. It formed 4.6 billion years ago, long before the bubble existed. But the Sun orbits the galaxy, and as it moves, it passes through different regions of the interstellar medium. About 5 to 10 million years ago, the Sun entered the local bubble, and we've been inside it ever since. This timing is interesting. The Sun entered the bubble after it formed, which means we avoided the supernova explosions that created it. If the Sun had been in the region when those explosions occurred, Earth might have been sterilized by the intense radiation. Supernovae release gamma rays, X-rays, and high-energy particles that can damage or destroy planetary atmospheres. A nearby supernova could strip away Earth's ozone layer, exposing the surface to deadly ultraviolet radiation from the Sun. Scientists estimate that a supernova within about 30 light-years of Earth could cause a mass extinction event. The radiation would deplete the ozone layer, allowing harmful UV radiation to reach the surface. This could kill phytoplankton in the oceans, disrupting the food chain, and cause widespread mutations and cancer in land animals. The fossil record shows several mass extinctions that might be linked to nearby supernovae, though the evidence is still debated. But we were spared. We entered the bubble after the explosions, and now we enjoy the benefits of living in a low-density region without having suffered the dangers of being too close to the events that created it. One benefit is reduced interaction with dense molecular clouds. These clouds are the coldest, densest regions of the interstellar medium, places where stars are actively forming. They're also chaotic environments, full of intense radiation from young hot stars, shock waves from stellar winds, and the occasional supernova. If the solar system passed through a dense molecular cloud, Earth's atmosphere could be compressed, heated, or eroded. The increased density could even affect the solar wind, the stream of charged particles that flows out from the Sun and helps protect Earth from cosmic rays. Inside the local bubble, we're far from these dangers. The nearest dense molecular clouds are tens or hundreds of light-years away, beyond the bubble's walls. We're in a quiet, stable region where the environmental conditions have remained relatively constant for millions of years. This stability might be one reason complex life was able to evolve on Earth. Life is resilient, but it's also sensitive to extreme environmental changes. If Earth had been repeatedly bombarded by radiation from nearby supernovae, or if the solar system had passed through multiple dense molecular clouds, life might have been set back or wiped out entirely. The fact that we've spent millions of years inside the local bubble, shielded from many of the galaxy's dangers, could be crucial to our existence. The local bubble is also interesting because it's not unique. Astronomers have identified other bubbles and superbubbles throughout the galaxy. The largest, like the North Polar Spur, a vast arc of hot gas visible in X-ray and radio observations, may be remnants of superbubbles that broke through the galactic disk and vented into the halo. The North Polar Spur is enormous, stretching hundreds of light years above the galactic plane. It was first detected in the 1950s through radio observations, but its nature remained mysterious for decades. Recent X-ray observations suggest it's part of a superbubble created by multiple supernovae in the galactic disk. The hot gas rose into the halo, creating the spur we see today. These superbubbles are important for the galaxy's structure. They redistribute matter and energy, create pressure that helps support the disk against gravitational collapse, and regulate star formation by both triggering it in some regions and suppressing it in others. The local bubble also interacts with the solar wind, the stream of charged particles flowing out from the sunday. The solar wind creates a protective bubble around the solar system called the heliosphere. This bubble shields the planets from most of the interstellar medium and cosmic rays. The boundary of the heliosphere, where the solar wind pressure balances the pressure from the interstellar medium, is called the heliopause. In 2012, Voyager 1 became the first human-made object to cross the heliopause and enter interstellar space. It's now measuring the properties of the interstellar medium directly, including its density, temperature, and magnetic field strength. The data reveals that the local bubble's properties are slightly different from what astronomers expected based on observations from Earth. The magnetic field is stronger, and the density is higher in some regions, suggesting the bubble has internal structure. Voyager 1, launched in 1977, has been traveling through space for over 45 years. It's now about 23 billion kilometers from Earth, so far away that radio signals take over 20 hours to reach us. The spacecraft is still sending back data, providing the first direct measurements of the interstellar medium. This information is invaluable for understanding the local bubble and how it affects the solar system. The Sun is moving through the local bubble at about 26 kilometers per second, relative to the surrounding interstellar medium. This motion means we're constantly encountering slightly different regions of the bubble as we travel. Over thousands of years, the properties of the interstellar medium near Earth change slightly, which could have subtle effects on the heliosphere and possibly even Earth's climate. Some scientists have proposed that passages through denser regions of the interstellar medium could compress the heliosphere, allowing more cosmic rays to reach Earth. Cosmic rays can affect atmospheric chemistry, potentially influencing cloud formation and climate. There's no strong evidence that this has caused major climate changes in the past, but it's an area of active research. The hypothesis is that cosmic rays ionize molecules in the atmosphere, creating condensation nuclei around which water droplets can form. More cosmic rays could mean more clouds, which would reflect more sunlight and cool the planet. Some researchers have proposed that variations in cosmic ray flux, caused by the solar system's motion through different regions of the interstellar medium, might explain some of the ice ages in Earth's history. But the evidence is still inconclusive. The local bubble won't last forever. Eventually, the hot gas will cool and mix with the surrounding medium. New supernova explosions might expand the bubble further, or create new bubbles that merge with it. And the Sun will eventually leave the bubble, passing into denser regions of the interstellar medium as it continues its orbit around the galaxy. But for now, we're in a stable, protective environment, a low-density cavity where the conditions are favorable for life. It's one more piece of the invisible architecture that makes our existence possible. And this bubble, this cavity in the gas, sits within a larger structure, the spiral arms of the Milky Way, which aren't solid features but waves of density that sweep through the disk, compressing gas and triggering star formation. Let's look at those arms now. If you've seen images of spiral galaxies, you know what spiral arms look like. Bright, curved structures radiating out from the galactic center, glowing with the light of millions of young stars. The Milky Way has spiral arms too, though mapping them from inside the galaxy is challenging. We think there are 4 major arms, or maybe 2 major arms and 2 minor arms, depending on how you count. But here's something that surprises most people. The spiral arms aren't permanent structures. They're not like the arms of a starfish, rigid and attached to the body. Instead, they're density waves, regions where stars and gas temporarily bunch together as they orbit the galactic center. Think of it like a traffic jam on a highway. Cars enter the jam from behind, slow down as they pass through, and then speed up again as they exit. The jam itself doesn't move much. It stays in roughly the same place. But the cars passing through are constantly changing. The spiral arms work the same way. Stars enter the arm, slow down slightly due to the increased gravitational pull, and then speed up again as they exit. The arm itself rotates more slowly than the stars, creating a lasting pattern that persists for hundreds of millions of years. This idea, called density wave theory, was developed by astronomers C.C. Lin and Frank Hsu in the 1960s. They were trying to explain why spiral patterns exist at all. If the arms were solid structures rotating with the stars, they would wind up over time wrapping tighter and tighter around the galactic center until they disappeared. But spiral galaxies don't do that. The arms stay distinct, which means they must be something other than solid structures. Lin and Hsu proposed that spiral arms are density waves, compressions in the disk that rotate more slowly than the stars themselves. These waves are sustained by the galaxy's gravity and rotation. As stars orbit, they feel the gravitational pull of the arms, which slows them down as they enter and speeds them up as they exit. This creates a traffic jam effect, bunching stars together in the arms. The mathematics behind this is elegant. The density wave moves at what's called the pattern speed, which remains constant at all radii. But stars at different distances from the galactic center have different orbital speeds. This means that at certain radii, stars move faster than the pattern, while at others, they move slower. The locations where stars and the density wave move at the same speed are called corrotation radii, and they're important for understanding where spiral arms can persist. The mathematical model they developed showed that these density waves are self-sustaining. Once established, they persist for billions of years, rotating at a constant pattern speed. The pattern speed is slower than the orbital speed of stars at most radii, which is why stars pass through the arms rather than staying in them. The arms are visible because they're regions of enhanced star formation. When gas enters an arm, it's compressed by the density wave. This compression triggers the collapse of molecular clouds, creating new stars. The most massive of these stars are hot and blue, and they shine brightly, illuminating the arm. These massive stars don't live long, just a few million years, so they don't have time to leave the arm before they die. This is why spiral arms appear blue in photographs. They're full of young, hot stars that are born and die without ever leaving the density wave. Stars like our Sun, which live for billions of years, pass through spiral arms multiple times during their lives. The Sun probably passes through a major arm roughly once every 100 million years. During these passages, the solar system experiences a slightly denser environment, with more gas, dust, and nearby stars. This could have subtle effects on Earth's climate, or the rate of comet impacts, though the evidence for this is still uncertain. Some scientists have proposed that passages through spiral arms might trigger ice ages or mass extinctions on Earth. The idea is that the increased density in spiral arms might disturb comets in the outer solar system, sending some of them into the inner solar system where they could impact Earth. Additionally, the higher rate of star formation in spiral arms means more supernovae, which could expose Earth to increased radiation. However, the evidence for these effects is weak, and most scientists think the Sun's location between major arms has kept us relatively safe. Recent data from the Gaia mission, which has measured the positions and motions of over 1 billion stars with unprecedented precision, has revealed new details about the spiral arms. The arms aren't smooth. They have substructure, spurs and branches where gas is being funneled in particular directions. Our Sun sits in one of these spurs called the Orion Spur, or local arm, which connects two major arms. The Gaia data, released in multiple batches starting in 2016, has revolutionized our understanding of the Milky Way's structure. By measuring the parallax of stars, tiny shifts in their apparent position as Earth orbits the Sun, Gaia has determined the distances to over 1 billion stars with incredible accuracy. This has allowed astronomers to create three-dimensional maps of the galaxy, showing the spiral arms in unprecedented detail. The density waves that create spiral arms are driven by resonances in the galactic disk. A resonance occurs when the orbital period of a star matches some multiple of the rotation period of a wave or pattern. At these special locations, the star feels a repeated gravitational tug at the same point in its orbit, which amplifies the wave. The locations of spiral arms are determined by where these resonances occur. The galactic bar, a rectangular structure of stars and gas at the center of the Milky Way, also plays a role in maintaining the spiral arms. The bar rotates as a rigid body, and its gravitational influence extends far into the disk. This influence creates resonances that help drive and sustain the spiral density waves. The galactic bar is about 27,000 light-years long and rotates once every 200 million years or so. It's younger than the galaxy itself, probably forming within the past few billion years. Bars are common in spiral galaxies. About 2/3 of all spirals have bars, suggesting they're a natural phase in galactic evolution. Not all galaxies have spiral arms. Elliptical galaxies, which form from the merger of two spiral galaxies, are smooth and featureless. Irregular galaxies, like the Magellanic Clouds, lack organized structure. Spiral galaxies, like the Milky Way, are special because they have the right combination of rotation, gas content, and gravitational stability to maintain density waves. The spiral arms are also sites where the galactic magnetic field is strongest. As gas is compressed in the arms, the magnetic field is compressed too, amplifying its strength. This stronger magnetic field affects star formation, providing additional pressure that can either support molecular clouds against collapse or, in some cases, channel the collapse along field lines. The arms also play a role in the galactic fountain process we discussed earlier. Star formation in the arms produces massive stars that explode as supernovae. These explosions inject energy into the interstellar medium, heating gas and driving winds that vent into the halo. The gas cools, falls back onto the disk, and the cycle continues. So when you look at an image of a spiral galaxy, you're seeing more than just stars. You're seeing a dynamic structure, a wave pattern shaped by gravity and rotation, a place where gas is compressed, stars are born, and energy is released back into the galaxy. The arms are temporary gatherings, not permanent features, but they're crucial for regulating star formation and shaping the galaxy's appearance. Our Sun's location in a minor spur between two major arms is relatively calm. We're not in the thick of a major star-forming region, which means fewer nearby supernova explosions and fewer massive stars that could pose a threat. This quiet location, combined with the protective local bubble, gives Earth a stable environment where life can thrive. The spiral structure of the Milky Way is maintained by a delicate balance of forces. If the galaxy were rotating too quickly, the centrifugal force would overcome gravity and the disk would fly apart. If it were rotating too slowly, gravity would pull everything into the center. The actual rotation rate is just right to maintain a stable disk with long-lived spiral arms. And this structure, these spiral arms sweeping through the disk, are connected to something deeper, a flow of matter and energy driven by the galactic center, where a supermassive black hole sits, shaping the core of the galaxy. Let's turn our attention there now. At the very center of the Milky Way, 26,000 light-years from Earth, sits a supermassive black hole. It's called Sagittarius A star, pronounced Sagittarius A star, and it's 4 million times the mass of the Sun. This black hole is the gravitational anchor of the galaxy, and its influence extends far beyond the immediate vicinity of the galactic center. Black holes get a reputation as cosmic vacuum cleaners, sucking up everything around them. But that's not quite accurate. A black hole's gravity is strong, but only extremely close to the black hole itself. At a distance, a black hole's gravity is no different from the gravity of any other object with the same mass. If the Sun were suddenly replaced by a black hole with the same mass, Earth's orbit wouldn't change. We'd keep orbiting at the same distance, just in darkness. Sagittarius A star is quiet by supermassive black hole standards. It's not actively consuming large amounts of matter. Instead, it sips small amounts of gas that drift too close. Current estimates suggest the black hole is accreting matter at a rate of only about 1/10,000th of a solar mass per year. That sounds like a lot. But for a black hole of its size, it's incredibly modest. If Sagittarius A star were consuming matter at the maximum theoretical rate, called the Eddington limit, it would be millions of times brighter than it currently is. The galaxy's center would blaze with X-rays and gamma rays, potentially making conditions harsh for life, even at our distance. But this quiet phase hasn't always been the case. Evidence suggests that a few million years ago, the black hole was much more active. That evidence comes from structures called the Fermi bubbles. These are vast lobes of high-energy gamma-ray emission, extending 25,000 light-years above and below the galactic plane. They were discovered in 2010 by NASA's Fermi Gamma-Ray Space Telescope, which maps the sky in gamma rays, the highest energy form of light. The discovery was unexpected. Astronomers had been analyzing data from Fermi for months, trying to understand the diffuse gamma-ray emission from the Milky Way. When they subtracted the known sources, they found these enormous structures extending far above and below the galactic center. The bubbles are so large they cover a huge fraction of the sky, yet they had been missed because they blend into the background glow. The Fermi bubbles are thought to be remnants of a massive outburst from the galactic center, perhaps triggered by Sagittarius A star consuming a large gas cloud or tearing apart a star. The energy release was enormous, inflating these bubbles and heating gas to millions of degrees. The gamma rays we see today are produced by high-energy particles, likely accelerated in the original outburst, interacting with gas and light in the bubbles. Similar bubbles have been detected in X-rays by satellites like Eurosita, a German-Russian X-ray telescope that launched in 2019. The X-ray bubbles have sharp edges and complex structure, suggesting the outburst that created them was directional, possibly involving jets of matter blasted out along the black hole's rotation axis. These outbursts are part of the galactic center's larger role in regulating the galaxy. When a supermassive black hole feeds actively, it releases enormous amounts of energy, heating the surrounding gas and driving powerful winds that can blow gas out of the galaxy entirely. This process, called feedback, prevents the black hole from growing indefinitely and also regulates star formation in the central regions of the galaxy. Without feedback, the galactic center would be forming stars much more rapidly than it does. The gas density there is high enough that stars should be forming constantly, but observations show that star formation in the central few hundred light-years is actually relatively modest. The energy from Sagittarius A star, even during quiet periods, heats the gas enough to prevent most of it from collapsing into stars. The region immediately around Sagittarius A star is one of the most extreme environments in the galaxy. The density of stars there is millions of times higher than in our solar neighborhood. Stars pass within light days or light hours of each other, close enough that gravitational interactions are common. Some stars are flung outward at incredible speeds, becoming hypervelocity stars that can escape the galaxy entirely. Others spiral inward, eventually crossing the event horizon and disappearing forever. Hypervelocity stars are fascinating objects. They're traveling at speeds of over 1,000 kilometers per second, fast enough to escape the Milky Way's gravity. Astronomers have found several dozen of these stars, most of which originated in the galactic center. The leading theory is that they were once part of binary star systems that ventured too close to Sagittarius A star. The black hole's gravity tore the binary apart, flinging one star outward at high speed while capturing the other. Astronomers have tracked individual stars orbiting Sagittarius A star, measuring their speeds and distances with incredible precision. One star, called S2, completes its orbit in just 16 years, swinging so close to the black hole that it reaches a significant fraction of the speed of light. During its closest approach, relativistic effects become measurable. Time runs slightly slower for S2 than for more distant objects, exactly as Einstein's general relativity predicts. The observations of S2's orbit have provided some of the best tests of general relativity in strong gravitational fields. In 2018, when S2 made its closest approach to Sagittarius A star, astronomers detected the gravitational redshift of light from the star. The light was stretched to longer wavelengths as it climbed out of the black hole's gravitational well, exactly as predicted by Einstein's equations. In 2022, the Event Horizon Telescope collaboration released the first image of Sagittarius A star. Well, not the black hole itself, which emits no light, but the glowing ring of superheated gas swirling around it. The image showed a dark circle, the shadow of the black hole, surrounded by a bright, asymmetric ring. This was the second black hole ever photographed, after the one at the center of the galaxy, M87, and it confirmed that our own galaxy's heart looks much like we expected. The Event Horizon Telescope isn't a single telescope, but a network of radio telescopes scattered around the world, from Hawaii to Chile to Antarctica. By combining observations from all these telescopes, astronomers created a virtual telescope the size of Earth, achieving the resolution needed to image the immediate vicinity of Sagittarius A star. The gas swirling around Sagittarius A star is part of an accretion disk, a flattened structure where matter spirals inward toward the black hole. As the gas falls, it heats up due to friction and compression, reaching millions of degrees and emitting X-rays. But Sagittarius A star is consuming matter very slowly. The accretion disk is thin and inefficient, which is why the black hole is so quiet compared to active galactic nuclei in other galaxies. Some active galactic nuclei are so bright they outshine their entire host galaxy. These are called quasars, and they're powered by supermassive black holes, consuming vast amounts of gas and emitting jets of particles traveling near the speed of light. Sagittarius A star doesn't do this now, but it might have in the past, and it could again if a large gas cloud or star wanders too close. Quasars were much more common in the early universe. When astronomers look at distant galaxies, they're seeing them as they were billions of years ago, because light takes time to travel. The farther away a galaxy is, the longer its light has been traveling, and the farther back in time we're seeing it. Observations show that quasars were most common when the universe was a few billion years old. As galaxies matured and consumed or expelled their gas, quasar activity declined. Today, most supermassive black holes are quiescent, like Sagittarius A star. The galactic center is also home to a cluster of massive young stars, which is puzzling. The tidal forces near a supermassive black hole should prevent star formation in the immediate vicinity. How these stars came to be so close to Sagittarius? A star is an open question. One theory is that they formed farther out and migrated inward through gravitational interactions. Another is that they formed in a brief period when conditions were favorable, perhaps in a massive disk of gas that temporarily surrounded the black hole. The galactic center is surrounded by a nuclear bulge, a spherical region densely packed with older stars. This bulge contains about 10 billion stars and extends several thousand light-years from the center. Beyond the bulge, the galactic bar, a rectangular structure of stars and gas, connects the bulge to the spiral arms. The bar is important for the galaxy's dynamics. It rotates more slowly than the disk, and its gravitational influence channels gas inward toward the center. This inward flow of gas feeds star formation in the central regions and occasionally delivers gas to Sagittarius A star, triggering periods of activity. The Fermi bubbles, the outflows from past activity, and the current quiet state of Sagittarius A star all tell us that the galactic center is variable. It cycles between active and quiet phases, driven by the availability of gas to feed the black hole. Right now, we're in a quiet phase, but that could change. And beyond the galactic center, beyond the visible disk, there's another component of the galaxy's architecture that we rarely think about. A vast halo of hot gas surrounding the entire galaxy, storing matter for future star formation. Let's explore that halo now. If you could see X-rays, the Milky Way would look very different. The spiral disk of stars would be there, but surrounding it would be an enormous sphere of glowing gas extending 1 million light-years or more from the galactic center. This is the galactic corona, a hot halo of ionized gas that contains as much mass as all the stars in the disk combined. The corona is incredibly hot, about 1 million degrees Kelvin. At these temperatures, hydrogen is fully ionized, meaning the electrons have been stripped away from the protons. The gas is so hot that it emits X-rays, which is how astronomers detected it in the first place. But the corona is also incredibly diffuse. The density is about 1 particle per 1,000 cubic centimeters, far lower than the interstellar medium in the disk. This makes it difficult to observe. The X-ray emission is faint, spread over a huge area, and easily confused with other sources of X-rays, like distant galaxies or hot gas in galaxy clusters. Despite these challenges, astronomers have confirmed the corona's existence through multiple observations. Satellites like Chandra, XMM Newton, and the recently launched eRosetta have detected diffuse X-ray emission around the Milky Way and other spiral galaxies. By measuring the properties of this emission, astronomers can estimate the temperature, density, and total mass of the corona. The Chandra X-ray Observatory, launched by NASA in 1999, has been particularly important for studying the galactic corona. Its high-resolution instruments can distinguish faint diffuse emission from point sources, allowing astronomers to map the hot gas around the Milky Way. The corona formed from gas that fell into the Milky Way's dark matter halo, but didn't cool and settle into the disk. When gas falls into a dark matter halo, it gets compressed and heated by the halo's gravity. If the gas cools quickly, it can lose energy through radiation and fall inward, eventually settling into a rotating disk. But if the gas doesn't cool fast enough, it stays hot and remains in the halo. The cooling time depends on the density and temperature of the gas. In the dense inner regions of the halo, gas cools relatively quickly and rains down onto the disk. But in the outer regions, where the density is lower, the cooling time can be longer than the age of the universe. This gas remains hot, forming the corona we observe. The corona is this gas, sitting in a hot, extended reservoir around the galaxy. It's not just sitting still, though. It's constantly interacting with the disk. Gas from the disk, heated by supernova explosions and stellar winds, vents into the corona. This gas eventually cools and falls back onto the disk, completing the galactic fountain cycle we discussed earlier. The corona also serves as a reservoir for future star formation. Over billions of years, gas in the corona will slowly cool and accrete onto the disk, providing fresh material for new stars. Without the corona, the disk would run out of gas relatively quickly and star formation would stop. The corona extends the galaxy's lifespan, allowing star formation to continue for billions of years longer than it otherwise would. Recent observations have revealed structure within the corona. eROSITA, which mapped the entire sky in X-rays with unprecedented sensitivity, detected large bubbles and filaments in the hot gas. Some of these structures are connected to the Fermi bubbles, suggesting they were created by the same outburst from the galactic center. Others might be remnants of superbubbles from the disk that broke through into the halo. The eROSITA mission, launched in 2019 aboard a Russian spacecraft, completed its first all-sky survey in 2020. The data revealed structures in the hot gas that had never been seen before, including extensions of the Fermi bubbles in X-rays and numerous superbubbles breaking through the disk into the halo. These structures tell us that the corona isn't a smooth, static sphere. It's dynamic, shaped by energy input from the disk and galactic center, and by cooling processes that cause gas to condense and rain back down. The corona is also important for understanding the galaxy's missing baryon problem. Baryons are normal matter, the protons and neutrons that make up atoms. Based on observations of the early universe, particularly the cosmic microwave background radiation, we know how much baryonic matter should exist. But when we add up all the baryons we can see in stars, gas, and dust, we only account for about half of what should be there. The rest is missing. The galactic corona is one place where these missing baryons might be hiding. The hot, diffuse gas is difficult to detect, and it's possible that a significant fraction of the galaxy's baryonic mass is sitting in this hot halo, invisible to most telescopes. Another possibility is that the missing baryons are in an even hotter, more diffuse phase, too tenuous to emit detectable radiation. Or they might be in the warm, hot intergalactic medium, gas that fills the space between galaxies and is heated to temperatures between 100,000 and 10 million Kelvin. This gas is extraordinarily difficult to observe, but it might contain a large fraction of the universe's missing baryons. The corona also interacts with the cosmic web. Gas from the dark matter filaments that feed the Milky Way enters the halo as part of the corona. This gas is shock-heated as it falls in, reaching the corona's high temperatures Over time, it cools and settles into the disk, but while it's in the corona, it contributes to the hot halo's mass. The study of the galactic corona is still relatively new, and there's much we don't know. How much mass does it contain? How does it cool and accrete onto the disk? What role does it play in regulating star formation? These are active areas of research, and future X-ray missions will help answer them. What's clear is that the corona is an essential part of the galaxy's architecture. It's a reservoir of gas, a buffer between the cosmic web and the disk, and a recycling system that extends the galaxy's lifespan. Without it, the Milky Way would be very different. The corona also connects the galaxy to the larger cosmic environment. It's not an isolated system, but part of the continuous flow of matter from the cosmic web into galaxies. Understanding the corona means understanding how galaxies acquire and process gas over cosmic time. And this corona, this hot halo, doesn't exist in isolation. It's connected to the larger cosmic web, part of a network of filaments and voids that spans the universe. Let's zoom out now and see how the Milky Way fits into that larger structure. If you could see the universe on the largest scales, you'd see that it's not uniform. Galaxies aren't randomly scattered. They cluster along filaments, vast threads of matter stretching hundreds of millions of light years across space. Between the filaments are voids, enormous regions with very few galaxies. This structure, the cosmic web, is the largest pattern in the universe. The cosmic web formed from tiny density fluctuations in the early universe. Just after the Big Bang, matter was spread almost evenly, but not perfectly. Some regions were slightly denser than others, and these tiny differences grew over time. Gravity pulled matter from less dense regions into denser ones, creating a network of filaments with voids in between. Dark matter, because it doesn't interact with light or normal matter except through gravity, collapsed first. It formed the skeleton of the cosmic web, the filaments where galaxies would later form. Normal matter followed, falling into the dark matter filaments and settling into galaxies. The Milky Way sits on one of these filaments. If you could zoom out far enough, you'd see that our local group of galaxies is part of a larger structure called the Laniakea supercluster. This is a collection of about 100,000 galaxies spread across 520 million light-years. The Milky Way sits on the outskirts of Laniakea, on a filament that connects us to the Virgo supercluster, the nearest large concentration of galaxies. The name Laniakea comes from Hawaiian and means immeasurable heaven. It was chosen by the astronomers who mapped this supercluster in 2014, led by Brent Tully at the University of Hawaii. They traced the motions of thousands of galaxies and found that they all flow toward a common gravitational basin, defining the extent of the supercluster. Virgo is about 65 million light-years away and contains thousands of galaxies. It's pulling on the Milky Way and the rest of the local group with its gravity. We're falling toward Virgo at about 600 kilometers per second. This motion won't result in a collision, though. The universe is expanding, driven by dark energy, and that expansion is carrying distant structures away from us faster than gravity can pull them together. Virgo is close enough that gravity dominates, so we're falling toward it, but more distant superclusters are receding. The cosmic web isn't static. It's evolving, shaped by the competing forces of gravity and dark energy. In the early universe, gravity dominated. Matter clumped together, forming filaments and galaxy clusters. But as the universe expanded, dark energy became more important. Dark energy is a mysterious force that causes the expansion of space itself to accelerate. It counteracts gravity on large scales, preventing new structures from forming and gradually pulling existing structures apart. Over billions of years, dark energy will win. The filaments of the cosmic web will stretch and thin. Galaxies will become more isolated as the space between them expands faster than light can travel. Eventually, distant galaxies will disappear beyond our cosmic horizon, their light redshifted to infinity by the expansion of space. But that's trillions of years in the future. For now, the cosmic web is still intact, and galaxies are still connected by filaments. These filaments are highways for matter. Gas flows along them, channeled by the gravitational pull of dark matter. When a filament connects a galaxy to a large reservoir of gas, the galaxy grows quickly, forming new stars. When the filament runs dry, star formation slows. The Milky Way has been connected to active filaments for most of its history, which is why it's been able to form stars continuously for billions of years. But observations show that the rate of star formation in our galaxy has been declining over the past few billion years. This is partly because the galaxy is running out of gas, and partly because the cosmic web is aging. The filaments feeding the Milky Way are becoming more diffuse, delivering less gas. In another 5 to 10 billion years, star formation in the Milky Way will slow to a trickle. Eventually, it will stop altogether. The galaxy will become a collection of aging stars, with no new stars being born to replace those that die. The cosmic web also determines where galaxies form. Observations of the early universe using telescopes like the James Webb Space Telescope show that galaxies formed along dark matter filaments even when the universe was less than 1 billion years old. These early galaxies were small and irregular, but they grew through mergers, eventually forming the large spiral and elliptical galaxies we see today. The James Webb Space Telescope, launched in December 2021, has revolutionized our view of the early universe. Its infrared instruments can see through dust and detect light from the first galaxies, revealing how structure formed in the cosmic web billions of years ago. The Milky Way formed this way, through the merger of many smaller galaxies. Evidence of these ancient mergers is written in the motions and chemical compositions of stars in the halo and thick disk. By studying these stars, astronomers can reconstruct the Milky Way's formation history, identifying when and where mergers occurred. The cosmic web also influences the distribution of dark matter. Computer simulations show that dark matter isn't distributed evenly within galaxy halos. It's clumpier near filaments and smoother in voids. These variations in dark matter density affect how galaxies form and evolve. The existence of the cosmic web raises questions about the nature of dark matter itself. The web's structure depends on dark matter being cold, meaning the particles move slowly compared to the speed of light. If dark matter were hot, meaning the particles move at relativistic speeds, the web would look very different. Hot dark matter would wash out small-scale structure, preventing the formation of galaxies and filaments. Observations confirm that dark matter must be cold, which rules out certain candidates like neutrinos, which are too light and fast. The leading candidates are WIMPs and axions, both of which would be cold and interact very weakly with normal matter. The cosmic web is also a testing ground for cosmological theories. By comparing the observed structure of the web to predictions from simulations, astronomers can test models of dark matter, dark energy, and the early universe. So far, the standard model, lambda CDM, agrees well with observations. But there are some puzzles, like the missing satellite problem and the too big to fail problem, which suggest that our understanding of dark matter might not be complete. The missing satellite problem refers to the fact that simulations predict many more small dark matter halos around the Milky Way than we observe as satellite galaxies. Either these halos exist but fail to form stars, making them invisible, or something about our dark matter model is wrong. The too big to fail problem refers to the fact that the most massive satellite dark matter halos predicted by simulations should host bright galaxies, but we don't observe them. These puzzles are driving new research into the nature of dark matter. The cosmic web connects everything. Every galaxy, including the Milky Way, is part of this vast structure. The filaments that feed us, the voids that surround us, the dark matter that holds it all together, they're all part of the same cosmic architecture. And this architecture is evolving. Star formation is slowing. Filaments are thinning. Dark energy is pulling the universe apart. The future of the Milky Way is shaped by this evolution. The Milky Way won't look the same forever. Star formation, the process that has been creating new stars for billions of years, is slowing down. And in the far future, it will stop completely. Right now, the Milky Way forms about 1 to 2 solar masses of new stars every year. That might not sound like much, but over millions of years, it adds up to billions of stars. But this rate has been declining for the past few billion years, and observations show it will continue to decline. The reason is simple. The galaxy is running out of gas. Stars form from cold molecular clouds in the interstellar medium. These clouds are made mostly of hydrogen, with some helium and trace amounts of heavier elements. When a cloud becomes dense enough, gravity takes over, and the cloud collapses, fragmenting into smaller pieces that become individual stars. But there's a limited supply of cold gas. Some of it is locked up in stars that will never return it to the interstellar medium. Low-mass stars like red dwarfs live for trillions of years, far longer than the current age of the universe. Once hydrogen is turned into a red dwarf, it's essentially gone forever. Red dwarfs make up about 70% of all stars in the Milky Way. They're small, typically between 8% and 50% of the Sun's mass, and they burn their fuel incredibly slowly. The smallest red dwarfs will continue shining for tens of trillions of years, long after every other type of star has died. This means that a significant fraction of the galaxy's hydrogen is being permanently locked away in these long-lived stars. Other gas is expelled from the galaxy entirely. Supernova explosions and stellar winds heat gas to millions of degrees, driving it out of the disk and into the halo. Some of this gas cools and falls back, but some escapes the galaxy's gravity and is lost to intergalactic space. The cosmic web, which has been feeding the galaxy with fresh gas for billions of years, is also running dry. As the universe expands, the density of gas in the filaments decreases. Less gas flows into the Milky Way, which means less fuel for star formation. Computer simulations like Illustris TNG, which model the evolution of galaxies over cosmic time, predict that star formation in the Milky Way will decline significantly over the next 5 to 10 billion years. By the time the universe is 20 billion years old, about 6 billion years from now, the Milky Way will be forming very few new stars. Eventually, star formation will stop altogether. The galaxy will become a collection of aging stars, slowly fading as they run out of fuel. The most massive stars, which burn bright and die young, will be gone first. After 1 billion years, without new star formation, there will be no more blue giants, no more supernovae, no more regions of active star birth. The only stars left will be low-mass red dwarfs, orange dwarfs like the Sun, and the remnants of dead stars, white dwarfs, neutron stars, and black holes. The galaxy will dim, its light shifting from blue and white to red and orange, as the hot, short-lived stars disappear and only the cooler, long-lived stars remain. This process will take billions of years, but it's inevitable. The Milky Way's future is one of slow fading, a gradual transition from a vibrant, star-forming galaxy to a quiet, aging system. But before that happens, something dramatic will occur. In about 4.5 billion years, the Milky Way will collide with Andromeda, the nearest large spiral galaxy. Andromeda is heading toward us. Right now, it's about 2.5 million light-years away, but it's approaching at 110 kilometers per second. In 4.5 billion years, the two galaxies will collide. Well, collide isn't quite the right word. Galaxies don't collide like solid objects. They're mostly empty space. Stars are separated by such vast distances that the chances of two stars actually hitting each other during a galactic merger are incredibly small. Instead, the galaxies will pass through each other, their gravitational fields interacting, pulling stars, gas, and dust into chaotic new orbits. Computer simulations of the Milky Way-Andromeda merger show that the process will take about 2 billion years. The galaxies will approach, pass through each other, swing back around, and collide again. Each pass will strip away stars and gas, flinging some into intergalactic space and pulling others into the growing merged structure. Eventually, after multiple passes, the two galaxies will settle into a single, larger galaxy. The spiral structure of both the Milky Way and Andromeda will be destroyed, replaced by a smooth, elliptical galaxy that astronomers have playfully nicknamed Milkymeda. This isn't unusual. Galaxy mergers happen throughout the universe at all cosmic epochs. They're a key part of galaxy evolution. Most elliptical galaxies formed from the merger of two or more spiral galaxies. The Milky Way itself has consumed dozens of smaller galaxies over its lifetime, including the Gaia Enceladus galaxy about 10 billion years ago, and Andromeda has done the same. In fact, detailed studies of the stellar halo show evidence of at least 10 major merger events in the Milky Way's history, each contributing stars that now orbit in streams and shells around our galaxy. But this will be a major merger, two large galaxies of comparable mass coming together. It will completely reshape the structure of both systems. What will happen to the solar system during this merger? Probably nothing catastrophic. The Sun and Earth will be flung into a different orbit, possibly ending up in a different part of the merged galaxy. But the chances of a close encounter with another star are tiny. The solar system will likely survive the merger intact. However, there are other things to worry about. By the time the merger occurs, the Sun will be nearing the end of its life. In about 5 billion years, the Sun will exhaust the hydrogen in its core and begin fusing hydrogen in a shell around the core. This will cause the Sun to expand into a red giant, growing large enough to engulf Mercury and Venus, and possibly Earth. Even if Earth isn't swallowed, the intense heat from the red giant Sun will make the planet uninhabitable. The oceans will boil away, the atmosphere will be stripped, and the surface will become a molten hellscape. Any life that still exists on Earth will have to evacuate or perish. So by the time the Milky Way and Andromeda collide, Earth will likely already be dead, and the Sun will be a bloated red giant or a cooling white dwarf. Humanity, if it still exists, will have moved on to other star systems or evolved into something unrecognizable. The merger will trigger bursts of star formation. When the gas clouds from the two galaxies collide, they'll compress, heating up and collapsing into new stars. These starbursts will be brief but intense, creating millions of new stars over just a few million years. Some of these stars will be massive and they'll explode as supernovae, enriching the interstellar medium with heavy elements. But eventually, even this burst of star formation will end. The gas will be used up or expelled, and the merged galaxy will settle into a quiet, aging state, just like the Milky Way would have if it hadn't merged with Andromeda. The Milky Way-Andromeda merger is just one event in the ongoing evolution of the local group of galaxies. Other, smaller galaxies in the local group will also merge with Milkomeda over time. The Magellanic Clouds, Triangulum, and dozens of dwarf galaxies will all be absorbed, adding their stars to the growing elliptical structure. Billions of years from now, the local group will be a single, massive, elliptical galaxy, slowly fading as its stars age and die. And around it, the rest of the universe will be receding, driven away by the accelerating expansion of space. The long-term fate of Milkomeda is to become increasingly isolated. As the universe continues to expand, accelerated by dark energy, distant galaxy groups will be carried beyond our cosmic horizon. Eventually, Milkomeda will be alone in an observable universe that appears empty, surrounded by darkness. Let's zoom out one more time. Not just to the edge of the Milky Way, or the local group, or even the cosmic web. Let's zoom out to the entire observable universe and think about the far future. Trillions of years from now, the universe is 13.8 billion years old. That sounds ancient, but in terms of the universe's total lifespan, it's young. The universe has a very long future ahead of it. A future that will eventually be dark, cold, and empty. Right now, stars are still forming. Galaxies are still merging. The cosmic web is still visible, but this won't last. In about 100 billion years, the universe will look very different. The expansion driven by dark energy will have carried most galaxies beyond our cosmic horizon. The only galaxies we'll be able to see will be those in our local group, the ones gravitationally bound to us. Everything else will have disappeared, their light stretched to infinite wavelengths by the expansion of space. The merged galaxy, that was once the Milky Way and Andromeda, will be alone in an ocean of darkness, a single island of light in an otherwise empty universe. Star formation will have stopped long before this point. Without fresh gas from the cosmic web, galaxies will exhaust their fuel. The last stars will form, live, and die. The galaxy will dim, its light shifting to the red end of the spectrum as only the longest-lived, coolest stars remain. In 1 trillion years, even these stars will begin to die. Red dwarfs, which can live for trillions of years, will eventually exhaust their hydrogen and fade into white dwarfs. These white dwarfs will cool slowly, radiating away their remaining heat over countless eons, eventually becoming black dwarfs, cold, dark remnants, no longer emitting any light. By this point, the galaxy will be invisible. No stars will shine. The only objects left will be stellar remnants, white dwarfs, neutron stars, and black holes. And even these will slowly decay. White dwarfs will cool until they reach the temperature of the cosmic microwave background radiation, which will itself have cooled to near absolute zero due to the expansion of the universe. At that point, the white dwarfs will be indistinguishable from the background. Neutron stars will also cool, eventually becoming invisible. Black holes will evaporate. This process, predicted by Stephen Hawking in 1974, occurs because black holes emit a tiny amount of radiation due to quantum effects near the event horizon. For a stellar mass black hole, this Hawking radiation is incredibly faint, far too weak to detect with any current technology. But over unimaginable timescales, this radiation will carry away the black hole's mass. A solar mass black hole will evaporate in about 10 to the 67 years. A supermassive black hole like Sagittarius A's star will take 10 to the 100 years. These timescales are so long they're almost meaningless. The current age of the universe is only 10 to the 10 years. We're talking about timescales a trillion times longer. But given enough time, even black holes will disappear. And when they do, the universe will be left with only the most fundamental particles. Photons stretched to infinite wavelengths by the expansion of space. Neutrinos barely interacting with anything, and perhaps a few stray electrons and positrons. But even these particles might not last forever. Some theories predict that protons, which we currently believe are stable, might actually decay over extremely long timescales. If protons decay, then all the matter in the universe, every atom, will eventually disintegrate into radiation. This is called proton decay. And while it's never been observed, some theories of particle physics predict it should occur. The timescale for proton decay is thought to be at least 10 to the 34 years, far longer than the current age of the universe, but not infinite. If protons decay, then the final state of the universe will be a sea of photons and other massless particles, endlessly expanding, growing colder and more dilute, approaching absolute zero but never quite reaching it. This is the heat death of the universe, a state of maximum entropy, where no energy is available to do work, no structures can form, and nothing interesting can ever happen again. The universe will be uniform, empty, and dead. But there's something almost peaceful about it. The universe won't end in a violent collapse or a fiery explosion. It will simply fade away, slowly and quietly, over timescales so long that no mind could comprehend them. All the stars that ever shone, all the galaxies that ever formed, all the life that ever existed will be gone. Not destroyed, but dissipated. Their energy spread so thin across the expanding universe that nothing remains. The invisible architecture we've explored, the dark matter filaments, the cosmic web, the spiral arms, the galactic corona, all of it will be gone. The structures that once controlled where stars could exist, where galaxies could form, where life could arise, will dissolve into uniform darkness. The Milky Way, this beautiful spiral that has been our home, will be a memory. A pattern that existed for a few tens of billions of years in a universe that will continue for countless trillions more. And yet, here we are. In this brief moment of cosmic history, when stars still shine, galaxies still form, and life can exist, we live in a universe that still has structure, still has light, still has the possibility of meaning. The far future may seem bleak, but it also puts our present moment in perspective. We're living in what might be called the golden age of the universe, a time when structure exists, when stars shine, when planets form, and when life can emerge to contemplate it all. Think about what that means. The universe is 13.8 billion years old, but it will exist for trillions upon trillions of years. If you compress the entire lifetime of the universe into a single year, with the Big Bang happening on January 1st, we're living in early January. The first few days, everything that's happened so far, the formation of galaxies, the birth of stars, the evolution of life, all of it has occurred in this tiny sliver of cosmic time. The universe will spend most of its existence in darkness, empty, cold, and devoid of stars. The brief era when galaxies shine, when structure exists, when life is possible, that's the exception, not the rule. We happen to exist during this exceptional period, and even within this exceptional period, we're in a privileged location. Not every part of the Milky Way is hospitable to life. Not every star system sits in a protective bubble like the local bubble. Not every planet orbits in the habitable zone of a stable star. The series of circumstances that led to our existence is remarkable. The invisible architecture we've explored tonight isn't just an abstract cosmic structure, it's the reason you're here. Every element in your body was created in stars that were organized by this architecture. The sun formed in a location dictated by the flow of gas along dark matter filaments. Earth condensed from material enriched by the galactic fountain. Life evolved during a period of relative calm inside the local bubble, protected from the galaxy's most violent processes. This architecture is invisible, but it's more fundamental than anything we can see. The stars are temporary. They'll all die eventually. The galaxies will fade, but the laws of physics that created this architecture, the interplay of gravity and matter and energy that shaped the cosmic web, those principles are eternal. Understanding this architecture is one of humanity's greatest achievements. For thousands of years, we looked up at the Milky Way and saw only a river of light. We had no idea we were living inside it, embedded so deeply that we couldn't perceive its true shape. It took centuries of patient observation, brilliant theoretical work, and increasingly powerful telescopes to reveal the invisible structures that control our galaxy. And we're still discovering new layers. New missions are being planned, new telescopes are being built. The James Webb Space Telescope, launched just a few years ago, is already revealing details about the early universe that we never could have seen before. Future observatories will map dark matter with even greater precision. They'll trace the flow of gas through the cosmic web. They'll discover how galaxies formed in the first billion years after the Big Bang. Each discovery adds to our understanding of the invisible architecture. Each observation refines our models of how galaxies evolve, how stars form, how planetary systems develop. We're living in an age of cosmic discovery, piecing together the story of how we came to be. In the unimaginably distant future, when the universe is cold and dark, there will be no observers left to witness the emptiness. But right now, we're here, looking up at the stars, trying to understand the invisible architecture that makes our existence possible. We started this journey by asking, what controls every star in the Milky Way? And we found that the answer is invisible architecture. Dark matter filaments form the skeleton. Rivers of gas flow along them, bringing fuel for star formation. The local bubble provides a protective cavity. Spiral arms compress gas into stars. The galactic center shapes the flow of matter and energy. The corona stores gas for the future. And the cosmic web connects it all, linking our galaxy to the larger universe. Every star in the Milky Way exists where it does because of this architecture. The sun formed where it did because that's where gas was available. It orbits where it does because of the gravitational pull of dark matter. It's surrounded by the local bubble because ancient supernovae carved out this cavity. And it's moving through space, carried by the rotation of the galactic disk, the motion of the solar system through the local bubble, and the slow fall of the entire Milky Way toward the Virgo supercluster. This architecture isn't permanent. It's evolving. Star formation is declining. The cosmic web is stretching. In billions of years, the Milky Way will merge with Andromeda. And in trillions of years, everything will fade into darkness. But right now, in this moment, the architecture is still here. The invisible framework that makes our existence possible is still functioning. The dark matter is still holding the galaxy together. The gas is still flowing. Stars are still forming. And we, sitting on a rocky planet orbiting an ordinary star, get to witness it all. The Milky Way is more than just a collection of stars. It's a dynamic system, shaped by forces we can barely see, operating on scales that dwarf human comprehension. And understanding this system, mapping this invisible architecture, is one of the great achievements of modern astronomy. We've learned that we're not separate from the galaxy. We're part of it, made from its atoms, shaped by its history, dependent on its structure. The calcium in your bones was forged in a supernova billions of years ago, created when a dying star's core collapsed and rebounded in a catastrophic explosion. The oxygen you're breathing was created in the core of a massive star, fused from helium through nuclear reactions that required temperatures of hundreds of millions of degrees. The iron in your blood was scattered across light years before eventually condensing into the planet beneath your feet, likely created in a supernova that occurred when the galaxy was young. Even the hydrogen that makes up most of your body's water dates back to the first few minutes after the Big Bang, when the universe was hot and dense enough to forge the simplest atomic nuclei. You are stardust, organized by the invisible architecture of the galaxy into a pattern complex enough to look back and understand where it came from. And that's the final secret of the Milky Way. It's not just a galaxy, it's a story 13 billion years in the making, written in starlight and dark matter, shaped by gravity and time. A story that includes supernovae and black holes, spiral arms and cosmic webs, and somewhere in the middle of it all, us, looking up at the night sky, asking questions, trying to understand. The invisible architecture controlling every star in the Milky Way is also the architecture that makes our existence possible. An understanding that architecture is how we begin to understand ourselves. Thanks for joining me on this journey through the hidden structures that control our galaxy. If you found it interesting, a like or subscribe would mean a lot. It helps these videos reach more people who share our curiosity about the cosmos. And if you want to share where you are in the world right now, I'd love to know. Leave a comment below. We're all sitting on the same planet, orbiting the same star, held by the same galaxy, connected by the same invisible architecture. The Milky Way holds us, and we're beginning to understand how. Rest well, the spiral continues, turning slowly through the darkness, carrying you forward into the future. The invisible architecture remains, shaping the cosmos, guiding the flow of matter and energy, creating the conditions for stars to form and galaxies to evolve. And in this brief moment of cosmic time, you're here to witness it, to understand it, to be part of it. The architecture is invisible, but its effects are everywhere, in the stars above you, in the atoms that make up your body, in the story of how you came to be. The Milky Way's invisible architecture, the framework of creation, the skeleton of starlight, the foundation of everything we are. Good night.